Good afternoon. My name is Kostas Panos. I'm a professor of ECS and director of CITRIS, and I would like to welcome you to the 10th anniversary of the CITRIS Research Exchange, this forum. So we have hosted a remarkable lineup of technology innovators on the stage and are glad to see you all here today for the Spring 2019 series. Please join in welcoming our speaker today, Professor Prasant Mohapatra, Professor of Computer Sciences at UC Davis, but also Vice Chancellor of Research for University of California, Davis. Prasant today will be sharing his work on impactful research at UC Davis and innovative smart sensing. We ask you to please hold your questions until the end of the presentation. We'll have some time for that. But before I introduce the speaker, I would like to make a couple of announcements. Next week, as you all know, and I'm expecting a spring break, so we're not going to have the research exchange. We're going to continue on April 3rd, the week after that. And it will feature tech investigating reporter Cyrus Farivar of NBC News discussing his work on 50 years of surveillance law in America. So our speaker, Dr. Prasant Mohapatra, is a professor in the Department of Computer Science and serves as the Vice Chancellor for Research at the University of California, Davis. He is a former endowed chair of the Department of Computer Science. In the past, he has held visiting professor positions at AT&T, Intel Corporation, Panasonic Technologies, Institute of Infocom Research, I2R, in Singapore, and National ICT Australia. Also at the University of Padua in Italy, Korea Advanced Institute of Science and Technology, KAIST, in South Korea. So he traveled a lot. He was the editor-in-chief of the IEEE Transactions on Mobile Computing and has served on the editorial boards of several reputed journals. Dr. Mohapatra received his doctorate degree from Penn State and is the recipient of an Outstanding Engineering Alumni Award from Penn State University, and also an Outstanding Research Faculty Award from the College of Engineering at the University of California, Davis, and the HP Labs Innovation Research Award winner for 3 years. He's a fellow of the IEEE and AAAS, and his research interests are in the areas of wireless networks, mobile communications, sensor networks, and data analytics. Please welcome our speaker today.
Thanks, Kostas. That was a pretty generous introduction. It's certainly my pleasure to be over here. I have been associated as a faculty researcher in the CITRIS program at UC Davis since its inception, but ironically, I'd never visited the headquarters of CITRIS, so thank you for inviting me for this. I will have this talk in 2 parts. One as my role as Vice Chancellor of Research, and the other one as a researcher, a faculty pursuing research. I still have my research areas active. Someone was asking me the other day about, as Vice Chancellor of Research, I don't have to do that. Why am I doing it? The answer is that's how I maintain my health, my mental health. So that's the main thing. So first, with my hat as Vice Chancellor for Research, I want to give you an overview of the UC Davis research enterprise. We take pride at UC Davis. We take huge pride in multidisciplinary and interdisciplinary research activities. There's huge amount of collaboration across the universities and various areas, and it's one of the most comprehensive campuses. It's probably the most comprehensive UC campus in terms of the number of programs. We have more than 100 different programs in our campuses, more than 38,000 students and more than 23,000 staff and faculty. Again, if this numbers of staff and faculty look too big to you, that's mainly because we have a fairly big medical school, and that's where many of our staff are. We have 6 schools and colleges. Schools are the professional ones, and the colleges are the academic one, and you can see the entire list of it. Our current research funding is about close to 850 million of external funds. So it's a fairly large research enterprise. Again, I won't go through all the details over there. We make impact on the economy. We are rated pretty high in some of the areas, and I'll also provide you more view of that. Going one level down in terms of our research funding, there was a little bit dip over here, but in the middle, but since 2015, you can see that we are climbing and climbing at a very fast rate. We had a record-breaking year just last year for $847 million, and I'm hoping that that trend will continue as we move forward. And if you're interested further, where is our money coming from for research? Obviously, about half of them are coming from federal agencies, and you can see the other distribution. State contributes about 174 million out of the 747 million that we spend on research. Let me flash a few slides highlighting some of our research, examples of some of our research impacts. Okay, although I flash the money to you personally as Vice Chancellor of Research, I'm more interested in seeing what impact we make from our research enterprise. So I'll try to highlight a few of the impacts that we have made that have made the life easier for human beings and has stronger impact on societal needs. Back in 1940s, we were a lot of these things, honestly speaking, I learned after being the Vice Chancellor of Research. Back in 1940s, UC Davis was the first one to come up with this tomato harvesting vehicles, and with all the machineries, how you can automatically harvest the tomatoes without wasting them. So this had a significant impact in the economy of California as well as throughout the world in harvesting tomatoes without spoiling any of the tomatoes, and then again having a quicker turnaround rate. Another example over here is the plug-in hybrid. I'm sure many of you would be using plug-in hybrid, but you may or may not know we played a bigger role. Professor Andrew Frank, if you look up his if you search, is acknowledged as the father of plug-in hybrid vehicles, and that came out of UC Davis, where basically during that time, it might sound obvious to you now, that's where we kind of worked on combining the gasoline engines with the electric motors in the automobiles in order to create the plug-in hybrid vehicles. So there is a research center that was launched in 2007, which continued these activities over there. Another big impact that we had on the health side is Denofavir, which is a drug which, if you give to HIV-infected mothers, they will give birth to HIV-free infants, because prior to using this drug, HIV-infected moms, there was a very high probability of giving birth to infants which were HIV positive also. But using this drug, and this was a big discovery. Dr. Rompe's research at the Primate Research Center at UC Davis came up with this drug. We tested it, and it was FDA approved in 2001, and this has become the #1 HIV drug in the world. So this has a significant impact on the healthcare area. Again, one of the other areas that we take very high pride is the wine industry. So we do a lot of work. The wine industry, Professor Harold Olmo developed 30 grape varieties, and we have patents on some of those varieties, and we are kind of working a lot with the wine industry. Robert Mondavi Wine Institute, which is on campus, was possible because of a significant donation from Robert Mondavi from the Napa Valley area. And keep in mind, Robert Mondavi is not our alumni, but because of the potential of our impact on the wine industry, he chose to donate a sizable chunk of money to UC Davis. On the environmental side, protecting Lake Tahoe, that's another big aspect that we pursue. So we have again, many of you may not know, UC Davis has two big Davis is certainly the main campus. Medical campus is in Sacramento, but we have two satellite campus. So that's how we cover Sierra to the ocean. So we have a research center called Tahoe Environmental Research Center at Turk. We do a lot of work on there on maintaining the quality of water in Tahoe. So that has got a lot of impact on the environmental side. The plant immunity so this was an outcome of work from Professor Pamela Rowland. So basically here the idea is, again in simpler term, to identify the gene that can make the plants disease resistance. Okay, so this was a big finding in there. Just to show you the comparison of that, the discovery of these genes in animals led to a Nobel Prize in 2011. Okay, we didn't do the animal part, but the plant part was done at UC Davis. So that's another, again, these are some of the examples. This is another nice example on how we impacted an industry of close to $500 million in 2016. So the Holstein Bull, which is one of the popular breed, again, keep in mind, I'm originally from computer science. When I talk about health science, animal care and all, I'm a little bit rusty in those areas, so I have to recollect my thoughts for that. So this was one work where our researchers identified the mutation of the genes that was causing premature abortion in the cattle area, and which was costing about $500 million per year to that industry, and we identified the cause for that. This is probably the last example of our impact that I will show. This was all over in the press recently. UC Davis was the first, at UC Davis, we developed the first total body PET scanner. So the idea over here is the normal imaging technique where you do typically 15 to 20 centimeters per time, then you go through that enduring process in that machine for a long duration to get the entire scan. Our researchers have come up with a total body scanner, which again is very fast. The numbers might be somewhere over here. You can get the total body scan simultaneously, and that saves a lot of time, and also what I've been told that the clarity and the resolution is very high in this total body scanner. So this is another big impact over here. Again, these are just some of the highlights. I won't get into any more examples. Another one, anytime you eat strawberry, note that 80% of the strawberry that is consumed in the world, 80% of those varieties are out of the patent from UC Davis. So next time you eat strawberry, you are making a small contribution to UC Davis. Thank you for that. Okay, keep eating more strawberries. Some of our research strength. Precision medicine is, again, I won't go through the entire slides over here. I'll go through this really fast. So precision medicine is the intersection between the persons, their environment. So basically their genomics, so like phenomics almost in all the areas. So how do you come up with solutions or medicines that are kind of person specific, okay, very personal specific medicine? That's one goal of this. We have a fairly large number of faculty and researchers working on this topic related to sustainable energy and transportation. You must have heard about the Institute of Transportation Studies, where there is a lot of transportation related research done. We are in the process of currently bringing up all our energy related centers. We have renewable energies, we have water related energy, and many other types of energy work that are ongoing. We have researchers, I don't know whether I have listed over here, we also have researchers working on policy related to energy, environment and all. We are kind of putting everything together one umbrella, and want to create a larger, bigger energy institute. So yes, I have that Policy Institute for Energy, Environment and Economy. Food, again, food is, that's where the strawberries are. Food is one area that we are very emphatic about in our research enterprise, because it's almost certain, and you must have read it everywhere, with the growth in human population, we will, if we don't do anything now, by 2050 we will run out of food. I mean, this is kind of very well modeled out there. So this will be a huge challenge to the world. We are uniquely positioned to be a global leader in this area because of our strength in the agriculture area. So we have good expertise in plant science, genomics, nutrition, and we are embedding technology with it. And basically the goal is how we can use technology to revolutionize the sustainability of the food ecosystem. I mean, this is as important as we view as the importance of climate change. Okay, some people do not agree, but that's fine. But food and climate issues, these are two things that we are trying to pay very high emphasis. Moving on to the medical side, One Health is an approach that we are using in order to address the health of people, animals, plant, and kind of the entire and the environment. So basically, we call it as planetary health. Okay, so we want to package all this together and look at this in a pretty unified way. Obviously, you can see there is a very close relationship between animal health and human health, but we want to expand that by including the environmental factor. So, for example, the Center for Comparative Medicine, kind of blends the human health and animal health, and PREDICT, you may have heard about this, is a global surveillance for pathogens, and this is about a $200 million grant which UC Davis is leading for several different universities and institutions across the world. So basically, as the name indicates, how do you do, because pathogens don't have boundaries, they don't have nationalities or race, religion, culture, or anything, they are everywhere. Okay, how do you monitor these pathogens, and especially when you have an infectious stream of pathogens, how do you monitor them in a global scale? So that's a very big project that we are working on. Brain and aging is another aspect that we spend a lot of time on. So we have the Mind Institute, which takes care of neurodevelopmental disorders. A lot of interesting work going over there. Environment, I have talked about there, and we have, as I said, we have the big environmental research center on campus. Then we have two satellite ones, the Coastal Marine Science Institute in Bodega Bay and the Tahoe Environmental Research Center in the Tahoe area. In addition to this research, we also emphasize a lot on entrepreneurship and commercialization. We get close to $75 million per year from industry to support our research, and just last year's snapshot is we started 16 startups that graduated from our efforts. So what we do is we have programs where we provide, like Berkeley also, we provide small startup funds and help our faculty work with our students in order to incubate their ideas, and we help them in transforming that to the real world. Okay, so one last slide before I change course over here. The overall research, if you look at the big research units at UC Davis, the organized research units are the Air Quality Research Center, the Coastal Marine Science Institute, the Primate. The Primate Center is a national center. We have close to 5,000 monkeys that helps us in doing variety of research activities. Comprehensive Cancer Center, this is the Comprehensive Cancer Center is also a national designation, which I believe somewhere between 20 or 30 cancer centers in the nation have this designation. We have a healthcare policy research. This is based in Sacramento. ITS, I talked about it, the Transportation Studies, Institute of Environment, and we have, we are renaming this as a Global Nutrition Institute. So where we are focusing, and that's also one of my pet topic is, how do we provide nutrition to all parts of the world? There are many parts of the world where, people don't have resources or availability to have one meal per day. How do we address those issues? So that's one thing that we are looking over there. In addition to that, we have this concept called a special research program, where we also provide seed money for them to try out if they want to be a research center or not. Either way, it's not a failure. It's like, okay, let's try out whether we want to grow this way or have it in a small way or more or take another path in there. So there are multiple aspects, the outcome of these type of things. So this is kind of our, in the research center world, you can see that these are the startups that may graduate to this or something bigger or broader or whatever. So for example, I mean, as I said, we started this Center on Energy and Efficiency Institute. Now we want to make it bigger and broader in there. Innovation Institute for Food and Health, that's a pretty interesting innovation. So this is where we have a partnership with Mars, all the chocolates that you eat. So Mars has contributed close to $40 million over 10 years, and we are trying to, the whole idea of this institute is not on fundamental research, but how we transform a large chunk of research related to the food that we produce at UC Davis. How do we transfer it to the commercial world? That's the goal. So they provide also startup funds to for entrepreneurial purposes. Microbiome is one of our newest one, as the name indicates. We are looking more into the studies of microbiomes in there. Okay, so let me change gear a little bit over here, take off my hat as Vice Chancellor for Research and become a faculty in computer science. I want to give you a kind of a very high level view. Obviously, I have to finish this in 15-20 minutes, but let me quickly give you an overview of some of my current research effort, and this is not the full scope of work that I'm following, but something that I could harvest for a general type of audience. We are looking at smart sensing, and how do you do smart sensing with smart devices. So if you look around you, everything is becoming smarter and smarter, and probably at some point you'll think, am I the only one who's not becoming smarter? Okay. So you have smart chairs, smart lighting systems, smart thermostat, smart curtains, smart coffee makers, and many other things that you can think of nowadays, smart ties, and smart shoes, and I have all of those. So there are two aspects. One is your surrounding is becoming filled with those IoT type of devices which are becoming more and more smarter. You also have devices within your body, so you might be, at an average, and especially the college kids have several smart devices within their body. So you have, as I have listed over here, you can see you can have all these smart devices while you are walking around with you. So we have smart environment and smart devices within our body. How do we exploit it? So I'll give you a very high level view, and all this, I'll talk about 4 ideas in here. If you want more details, I have published papers in this, and all these 4 works resulted in 4 different patents also. They have been approved patents. So it's so I'll talk at a very high level. The first thing is, how do we get rid of pen and paper? Just use finger and air for our writing needs. Okay, so we have all these devices now. We have smartwatches and our smart bands. Many type of these devices. A lot more than that I know about. That the college kids are more familiar with this that we use. So the opportunity is, since we have a device in our hand anyway, can we use that for writing without using pen and paper? So basically, so what we say is, you can have different type of gestures. You can have arm gestures, you can have hand gestures, or you can have finger gestures. Okay, so there are 3 types of gestures that we are looking at. Can we do all these things? So to do our goal is, can we write just in the air? I have to keep a note now. Okay, call somebody, can I just write in the air and it gets saved somewhere? That's the goal. So first thing we wanted to start is, can we capture those gestures? So think about, and the other thing is, we are dealing with really small devices. So basically, your bands that you are wearing or watches don't have a keyboard or anything to enter things over there. And again, you have to also use fingers to enter the commands over there, fingers writing in the air to do that. So how do we do it? Again, this is not about, your, what is that Microsoft thing, Kinect or something, where you capture the video and you interpret. It's like real using the signals from your hand. So what we did is, we had a kit called Shimmer Kit. So we made those devices and to wear, and basically try to see how it works. So basically the main idea over here is, again, I'll just stay with the main ideas over here, is when you have a band in your hand, if I am changing my hand, whether my hand, my arm, hand, or fingers, there is energy in terms of kinetic energy, a real energy that you are spending, that can be captured by this device. And your movement creates unique signatures in the energy world, and this is what I wanted to show you. If you capture the energy from the accelerometers, all the devices have accelerometers which cost less than $1 nowadays. Okay, so if you capture the energy that is that you can calibrate through the accelerometers, and if you look at, so this is a simple thing. If I plot those, in the gyroscope energy and the accelerometers energy, I could see that there are 3 clusters in 3 different colors over here, and these colors tells me whether I'm moving my fingers or hand or arm. Okay, so similarly I can go through one more finer level granularity by, so we have looked at all these different types of gestures. Okay, I'm not going to read it, and we have found out that by using different classifiers or machine learning approaches, we have an accuracy of 90% or higher in interpreting these hand, arm, and finger gestures. Okay, that's a pretty high level of accuracy, maybe not 100%, but you can think of applications where you don't need 100%. The other thing is, if we started using, we wanted to see how we can capture these 3 locations. If you put these similar devices, we can see that when you do a finger gestures, it creates different signature, versus when you do a hand gesture, it creates distinct signature. So the whole idea over here is, when we plot the energy consumption in different types of motions, then we get unique signatures, and we can interpret that as a command in the system. Now, similarly, just to show you a little more finer granularity over there, it can also capture which finger you are moving. Okay, you can go into that finer granularity. The next step will be writing alphabets in the air and capturing it. And we don't, again, I skipped that part, but we do have results for, we are close to almost 90% accuracy in detecting English alphabets. Okay, there are a few challenges. We are ironing it out as we move forward. So that's one idea. Another idea, again, I'll go through it fast, is authentication. Any device that you use, you have to authenticate yourself. The username, password, that's the most common one, but we all know all the problems associated with that. But a few new ones are, you can use voice, you can use fingerprint. Voice is very inconvenient. If you want to check your email now, you will be hesitant to use voice because the room is so silent. Fingerprint needs additional hardware. So we wanted to look at the facial approach and how you can do this. Again, we are not talking about facial recognition. That part is pretty well solved by the image processing researchers. So we wanted to see if you are using your device in order to authenticate yourself, like, we did this work before iPhone 10, but if you're using iPhone 10, it gets the facial capture, and that's it. There are 2 problems to it. You can have 2D media attack or 3D attack. So some of these have been resolved by Apple. So 2D is, you take my picture, show my picture to your phone, you will get authenticated. That's called 2D attack. Toshiba came up with this approach that, okay, if we want to get rid of that, or Android 4.1 said you have to blink your eyes 2-3 times in order to get, so that it's not a picture. Works fine. However, I'm blinking my eyes so many times during this talk, you can record me and can use my video in order to bypass that. That's called 3D attack. Toshiba came up with a solution which works very well. Is you want to log in, it generates random command. Okay, move your head up, move down or left or right. It randomly generates. So you cannot have a pre-recorded one. It works the best. Okay, and that is the gold standard we'll compare. But the reason for which none of you guys use that is because it takes almost close to 30 seconds to 1 minute to get that thing done. If I tell you now to log in and it takes 30 seconds, you are doing this and this, or 1 minute, you will never do it. So it never got adopted anywhere. But that, in terms of results, that produces the best thing. But let me tell you what we did. We have this if you take your phone, basically, so the idea is, what is swiping, okay? We just swipe thing. I'm using swiping in a different thing. I'll say swipe your face. All you do is swipe your face like this. You hold your phone, swipe it. The only requirement, it has to cross the center point of your face. Okay, so there are 2 things that we are capturing in this. When you swipe your face, we want to do it pretty quick, because if we are not doing it quick, Toshiba has already found the best model. So we want to do it pretty quick. So when you are swiping it, it's actually not capturing anything other than an L thing from your face. This is your nose. Okay, so it just captures this L. It wants to make sure when you swipe it through, this L change angle. That will not happen if it is a static picture. Remember, we want to get rid of those 2D attacks, 3D attacks. So we want to, when you swipe it, this L will change the direction. That's how you make sure that it's not a 2D attack. The other thing, which is now thinking back, it's a pretty simple ideas. Again, all these things, we kind of quickly patented all these ideas. It's pretty interesting is what we do is, let me go over here, is when you are swiping, when I'm swiping across my face, it is capturing the recognition part, as I said, is done. It is just ensuring that this is a real thing that is happening now rather than recorded. What is happening is, irrespective of how carefully you do it, how strong or weak you are, you will have micro vibrations in your hand always. So when I'm swiping this, the micro vibrations are captured by accelerometers, and the micro vibration impacts those pixel movement. There is a correlation between the vibrations that is captured by the accelerometers and the movement of this pixel. That is the correlation we are using for authentication, and that is so strong that even you yourself cannot replicate from one swipe to the next swipe, because the vibration should be different. But that is not a problem, because the authentication is the correlation between those, and it will be very difficult for someone to break that. Okay, so that's the idea that's the main idea in this work. Again, I'm skipping quite a few slides just to show you. Again, don't read too much into it. Our performance is much better than any other scheme, but is as good as the one that the Toshiba produces. Now you might be thinking, okay, so what's the big deal? You got it as good as the Toshiba. The answer is over here. Your password, user ID password, takes about 4 to 5 seconds. The Toshiba takes about half a minute to a minute. We got the same result as your standard user ID and password with the level of security that the Toshiba provided at a much smaller time frame. Okay? So that's the main contribution of this. Again, you can use it as a multi-factor authentication over there. Couple other things that I want to highlight over here is we wanted to look at non-intrusive sensing. I want to sense you, and this is to address or kind of expose vulnerability related to privacies. Okay, so if I want to monitor you, then I have to put a smartwatch, or I have to take your phone or something. All these things have a lot of information about you. Now, if I want to do non-intrusive sensing, one thing we kind of assume that Wi-Fi is everywhere. Okay, so might as well capture that. So Wi-Fi, there is a concept called channel state information, which those of you from the area will know it very well. This is being captured at the access point, which monitors the current state of the channels. Okay, so the wireless channels. So this is, you can get it at the very fine ground. So this is not something where you have to invest time and money. It is out there. It is being captured and all. So the question is, can we use it? So what we did is, we wanted to do the gait analysis, GAIT. Each one of us has a unique walking style. That is the gait. Okay, so we wanted to see, can we use that unique, how do we capture that uniqueness in order to identify a person? And again, we ran experiments in the lab with our students. I have a good group of students, but have different gaits like all of us. So if you look at this, so if you take an individual, and all the results that I'm showing today, they're all experimental, nothing is simulated over here, is if you're taking a walk, take several times, you kind of, you can see that they are correlated, they kind of form a pattern. Each one of us has a pattern in walking style, and that pattern is also detectable by the CSI that your Wi-Fi access points are capturing. So, and you can see over here step 1 and step 2 similarly have expanded. If you have multiple steps, go with several different trials, you kind of form a pattern, and these curves will be different for different individual. And we have shown that they are quite distinguishable from varying from people to people. The only time, and we are still trying to figure out, get messes up is if you have a close buddy, you guys are walking together side by side, you can confuse the access point. But if you just run an experiments with individual walking, we found that there is significant difference between those. And if you look at different persons, so this is a chart showing, we tried 4 students, so you can see there is a clear distinction between there. You will not be confusing one student versus other, because the CSI captured from their walking styles are completely different. What CSI in simpler term does is, once you are walking, we are disrupting the signals, and that is being captured by the CSI. And the way you are disrupting is dependent on your walking style, and you can see it. You create distinct plots over here. Okay. Last thing I'll talk about, and this one, our the patent application for this got accepted yesterday only. So this is just coming out of the oven. So the idea over here, and I'll not use these slides very much, is for IoT devices. These are starved for energy. There is not much battery power in order to run many of the devices, or you want to save, because the battery dies, the device is thrown out. So we want to see how we can do that. So many of these devices that you have, they are low cost, and you can have right now, the Amazon speakers are a little bigger. You can make it micro size and so on. So the question here is, in many of these devices, like in my watch and all, if I can give commands through voice, but right now it knows, although it is hearing my voice, it knows I'm not giving command to it. So all these devices use a code word. If there is a Google device, you have to say, okay Google. That means okay, next voice is my command. Samsung uses Hi Galaxy. These devices know that. Like for example, your Alexa at your homes, Amazon Alexa, unless you say Alexa, the device knows that it's not for me. Okay, so this code word is kind of telling them, wake up. The next word is for a command for you. The challenge over this is they keep the microphone completely on, because they don't know when you will send a command to them. So as a result of which, there is continual uses of energy. So for example, in many of these devices, whether you are talking or not, the energy consumption is same because the microphone is on. Okay, so and most of the time, think about, you are using a device like Alexa. If your power, Alexa is not a good example because you will power it easily, but if you have a small IoT device that you use maybe 30 minutes per day, you have to run it 24 hours. So you are wasting a lot of battery in there. So we wanted to see how to address this issue. The microphone is a power hungry device over there. We went through the fine granular sensors in the devices. We found the accelerometers, they use very little energy, and because these are mechanical devices, that's not powered on all the time. So if you break open an accelerometers, feel free to do so. These are pretty cheap, at less than $1, as I said. They look somewhat like this. You have a solid thing and some kind of fingers embedded in there. So what happens is, these are stationary fingers, and when you have movement, that's how your phone accelerometer captures. This device, it's kind of moves, it vibrates or moves, and that's how the motion is captured. We studied and found out that that device is so sensitive that even acoustic voices can make it move to some extent. Now our goal is, can we use that to detect the hot word only? We don't need a complete voice recognition system by using accelerometer. If you can do it, fine, but you don't need that. So we figured out a way so that you can turn off your microphone completely and use the accelerometer or even the gyroscopes, because it is kind of the same mechanism, to detect your voice. So we said, when you say Hi Galaxy or OK Google or Alexa, that the acoustic vibration it creates, you make it learn the signature for that. Okay, and then basically looking at the movement of the accelerometers, so in a way you kind of break the notion of using microphone for voice recognition. You use accelerometer for voice recognition. What we achieved by that is, we looked at the power consumption over here. Let me skip those. Our power okay, first of all, it worked fine. We tried both male voice, female voice, and all and with different decibels in there, and the false positive rate was less than 5% or less than 10%. Okay, so most of the time it worked. But the big thing over here is, we tried with Google and Samsung phone, you have a savings of close to 50% in power consumption in these devices, which is a big savings when you are talking about IoT type of small devices, and that can be tuned further. Okay, so I am running out of time. This is my last slide, just to give you some of my personal views about where this area is leading to. Some of it or all of it could be wrong. I believe more and more sensing devices will be around us as we move forward. So we will be invaded with sensing devices around us, whether we are inside a building, outside the building, in a car, or in an airport or wherever we are, the number of sensing devices will grow at a very high rate. And with the same thing, there will be intelligent sensors. There will be a class of sensors. They will be intelligent in there, using the concept of AIs. They will learn who you are, and they will start to behave. The coffee machine will learn, you know, when each member of the family wants coffee and will prepare accordingly and all. So they will become, through the advances of AI, they will become more and more intelligent, and they will also adapt to the environment. Okay, the big challenges, and if you are a student, you know, if you are working in this area, you will be never out of business. Security and privacy will stay as one of the biggest challenges in this area. So there are no easy solutions for that. Precision sensing, this is where, you know, we will have an impact into the areas of health system, agriculture, and other, you know, solving the world food problem and all those things. Let me stop over here, and I'll be glad to take questions related to what I talked about UC Davis as well as my own research. So everything is within the scope. Thank you.
Thank you, Sergey. I get the privilege to get the microphone first. Thank you for a great talk. We should talk afterwards about passive Wi-Fi sensing. You have been doing quite a bit of this type of work for people counting and activity recognition. But I wanted to ask you, from an electrical engineer to computer science, is something that no one, neither of us would know very well. Mm-hmm. And this is the policy around GMOs, genetically modified organizations. Almost everything that we eat that is mass-produced is a GMO right now, but there is a very strong policy and sentiment against it. Can you reconcile the two? Can you just your thinking about that?
Yeah, so that's an interesting, but one of the most difficult question is the kind of the tension between GMO and non-GMO. If you think about it, if you look at the scale of the food problem that we are foreseeing for next 50 years or whatever, something needs to be done in order to address that. It will not solve itself automatically. GMO is one of the vehicles in there. What I would like to see is studies and more research being done that will negate the negative impacts of GMOs, but retain the positive part in terms of growth in food, but not all the, you know, making the organic inorganic. If we can solve that problem, then, you know, it will be a win-win for both the sides. It will be one of the most challenging problems as you can think of. Okay. Yes.
So a lot of what you're doing with these actuators looks like what you do with geophysical surveys and magnetic tellurics, seismic, and other stuff. And in that, they've gone from 2D versions to 3D versions. So ultimately, will you end up having actuators on one side of the room and the other, and being able to sort of model the difference and look at things in much more compelling and sophisticated ways?
Yeah. So actually, that's a good question. So we are kind of getting into a direction. I'll give you one example, and Ji Cheng is my student, worked on this also. So we were talking to Siemens about, you know, they make these generators which are hundreds of millions of dollars and all. Now it is very difficult to monitor the health of those generators. Like you can have finely, you know, nano level of cracks anywhere or kind of defects and all. So that creates a problem. So what we are trying now is, can we have non-intrusive detection of these type of things using high frequency? So we are trying 60 gigahertz and higher in order to blast those high frequency, in order to see, you know, if there is any variation in those frequency level, if there is a defect in there. We are also using it in multiple dimensions. You know, we did some work on, can you identify the quality of a vegetable or fruit through high frequency? You have, just think about it, you have a device like your iPhone, you go to the grocery store, you just flash it and it does the scanning and tells you whether this has appropriate level of water in it and all and everything. So we are looking at this three-dimensional sensing through very high frequency right now. So that's a good area to do more into that. The challenge is, once you go to high frequency, the example that you gave, outside the room it becomes a challenge because, you know, the penetration is very low. Other questions? Yes.
Thanks for the dual nature of your talk. With regard to your university responsibilities, Davis, you have the advantage of having a medical school,
Right.
As some other campuses don't.
Mm-hmm.
Would you have any? Although Davis does face the
Mm-hmm.
geographic challenge and the organizational challenge
Mm-hmm.
of distance, would you have any advice for organizing research, biomedical research in UCs that don't have medical schools?
Yeah. So, one of the things, first point that you said, I'm so clear about that. When I go and do my preaching in the medical school, I tell them that you guys don't realize what we have over here. Not many, existence of medical school in universities is not a given thing. It's only so many of them have it, and we have that, and that is a huge wealth that I hope our faculty realize that and exploit the advantage out of it. But if you think about it, the world is changing, and it's changing fast. And I gave this speech in the medical school. I went to the medical school to give a talk about computer science needs in medical school. I thought, very few people show up. 40 doctors showed up, so it was a pleasant surprise in there. But this is what I was preaching. The world is changing. If the medical school, they don't prepare or adapt to the changes, they will be left behind. For example, I said, will you be surprised if I tell that Google will be the next big healthcare provider? And I meant it, the way the world is moving, because many of the things are becoming more data driven. Of course, I was exaggerating a bit, but that is a threat in there. So how do we address that? So this is where a non-medical campus can work with the med schools at SF or at Davis and all, maybe to come up with solutions for the future where it will be a data-driven healthcare. Just think about it. I'll give you some numbers. If you look at the healthcare industry, it's a huge industry, much more than what we in engineering can even think of. Okay, it's orders of magnitude higher. However, 80% of the health-related expenses are related to chronic diseases. Chronic, the word is a time-dependent, is a time series thing. Devices like this, your cell phone spends with you 24/7, lot more time than anyone else, including your wife, spends with you. Think about your primary care physician, who, if you're lucky, spends only 15-20 minutes in a quarter with you. So these devices know a lot more about us than anyone else, even your doctor and all. But are we harvesting that information? Are the doctors harvesting that information to use it? Probably not. We have to figure out. So this is where the technology can meet the medical side, how we can harvest the huge data sets and even probably gather the data sets. I mean, the opportunity is huge. Walk into a hospital, if you go to the ICUs, being wireless researcher, I'm like, there are wires everywhere. Okay, do we really need it? There is like a jungle of wires in all these ICUs and all. Do we really need it? Probably not. So these are some of the areas we can work together with the medical schools. That's what it is. Other questions?
Well, if not, thank you very much
Thank
for
you.
an excellent presentation.